So as it says in the caption, we're going to be looking at tension in strings, only this time it's just one string. There's a second video with tension in two. So here's an example. You're holding a conker on the end of a piece of string. So the sources are forces, while the conker has a weight. Now that conker is in equilibrium, it's not accelerating. Therefore there must be an upward force equal to the weight of the conker. And that force will be provided by the tension in the string. Now, if it's you holding that conker on the end of a string, you will feel a force pulling down on you, and that force will be created by the tension in the string. Now, you may be tempted to think that what you are feeling is the weight of the conker. Weight only acts on the object itself, so the weight of the conker is only acting on the conker. However, because the conker has a weight, it creates a tension in the string, and the tension in the string, because the string is taut, the tensions are equal and opposite to each other at either ends of the string. So in actual fact, it's a tension in the string that you'd be feeling, albeit that tension has been created by the weight of the conker. And then it says, the string is taut, there are equal and opposite tensions in the string at each end, acting towards the centre. Now if we look at the forces only on the conker, then T must equal mg because the conker is in equilibrium. If we push the string to one side, so the conker is still in equilibrium but an angle of theta to the upward vertical, once again we've got a horizontal push force, P. Still got the weight of the conker, of course. And there are two tensions acting towards the centre of the string that are equal and opposite to each other. So if we resolve the tension that's acting on the conker, which is down here, we'll ignore this tension up here. The tension up here is acting on the person's hand, so not on the conker. So we're only interested in forces on the conker. So we're going to resolve this tension into its two components. T cos theta vertically, T sin theta horizontally. And therefore, we now have our horizontal and vertical forces giving us T sin theta must equal the push force P, and T cos theta must equal mg. And so here is our example. Sources of forces. We had a horizontal push force P. We've got the weight of the object, which it tells us is 2 kilograms, and we'll have an equal and opposite tension at either end of the string. So we resolve the tension on the mass. So it's T cos theta vertically, T sin theta horizontally. Then we've got P and the weight 2g, giving us our two equations. Horizontally, P equals T sin theta. Vertically, T cos theta equals 2g. From equation 2, we get the tension equals 2g divided by cos theta, and that's 22.6 newtons. And if we put that up into equation 1, that will give us P equals 11.3 newtons when rounded off. Just please note, when you're substituting your T back up here, don't use the rounded off version. We only round 1, so we use the full calculator answer here without rounding.